Welcome to the Plasma Frontier. Today we'll be discussing the third part of the toroidal fields. With us today is Patrick, Cleve, Fraz, and myself, Allison. Take it away, Fraz.
Yeah, thank you. And Joe's with us here today also.
Oh, Joe, I'm sorry.
That's okay, no problem. Basically, this is the third part of the toroidal field explanations. We're going to go into practical application and see if we can get some ideas of how we can predict what the fields look like before we actually put them together. I'm going to start with a few drawings, and we'll share my screen. It'll take a moment for that to come up. We're going to start with a basic circuit. This basic circuit is one we started, a couple months ago. And there we go. If we say the top of the screen is our positive coming in, and the bottom is our negative going out, simply because of definition. The in between these two is capacitors, or they can be simply plug and play connectors. And we notice that the plasma, or the current, is going to come in to each one of these, like so. When the capacitors fill, or the connection fills, then it travels on out the bottom in what we call negative. That's your basic premise. Now I'm going to go to the next image. I'm going to go through a bunch of images fast and furious here through this entire presentation, so bear with me as we cycle through these. Bringing up our next image. Reminds me I'm going to have to slow down so that the screens can pick up what I'm drawing. This is our second image. Now you notice across the top in red we have a whole series of little short arrows, and that's basically representing high frequency, many times per second impulses. Let's say we're harvesting from a big antenna coming in. That's our power supply, not a standard battery or a voltage, a controlled voltage supply. This is just a basically run-of-the-mill every day out in the sun with all the different impulses from the sun and other planets and radio waves, and everything that's in your environment gets collected onto this nano-coated wire. Nano-coating works really well because it's layers of carbon, and many, many layers of carbon, and they have humps and bumps and dips and crevices. And the wider the gap, the lower the longer frequencies can be picked up, and then the shorter the gap and the narrower the gap, the higher frequencies get picked up. They all get picked up into this wire and gets dumped into this circuit. So we call that positive because there's more of them on the top side. When it goes into this capacitor or the plug and play, which is that gap in the bottom, you see that light pink. Let me highlight, get my pen up. I'm going to draw it in purple. We're looking at that spot right there, and as the red arrows fill up, it fills up that space between the pin going down into it and the catcher's mitt on the outside edge, that cup. So it's filling that cup up, that capacitor up. In the plug and play, there's not much capacity, so it doesn't have a lot to fill, so it travels through fairly easy and quickly on its way to ground, which is on the negative. The interesting thing that happens is with the capacitance that's in these little cups along the way, they have to fill up before they discharge. And so we have a bunch of short little red arrows across the top, but we have fewer, larger, slower vibration pulses at the bottom. And so this starts setting up our heartbeat of our circuit, this pulse, this pop, 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 pop. The spot where we've got the capacitor, those could be also interpreted as a spark gap. You know, it has to build up behind it, discharges across the gap, and continues on. The bigger the storage, the longer it takes for that jump to happen, to go across the gap between the top, the positive, and the negative at the bottom. If we were to set up pickup coils, and we have one at the top there and one at the bottom, and we measured the difference, we'd actually have more at the top and less at the bottom. And so that difference, if we wanted to harvest off of this circuit, could be done by bypassing the capacitor and setting up something that had resistance, like an LED or a motor, and you may have to put another resistor on the discharge end before it went into, to make certain that it didn't empty all the capacitors at once. You just used once. Just one of those kind of interesting ideas, observation of the circuit. We end that one and pick up our next picture. Just a second for these to come up. Not only do we get this charge buildup. Let's see if I get my right. By building up a charge, look at this drawing to come up, it sets up a field. The larger the capacity of the capacitor in the middle, or you get some dynamics going, you start getting a production of a field. And we'll just pick this color. And you'll see in that circle, I've got the red arrows going in, the blue arrows coming out, simply because that's the direction that we're going in this particular drawing. But it sets up not just one, but in the case of these three capacitors, you actually have three fields that are being produced. And that's part of the reason why you can set up coils around either at the top edge or the bottom edge and pick up a difference in potential from one and the other. The difference in potential gives you the opportunity to do work in your electrical circuits. Basically, work is represented as watts. Okay, we'll stop sharing this one and go to the next one. And we're going to start working on this series is basically trying to set up your ability to perceive things in 3 dimensions. So that was the side view of that circuit. If we look at the same circuit from the top, it would look like this, slightly out of kilter. The top red one is that red wire going across to the center post. You see those dots in the center. And then the blue wire would be at the bottom, but if you look straight down, they just look like circles. Because the center is being pushed in, this is usually the expansion, which would be the magnetical, is going into the gravitational. The field is being contained in the inside. You see the blue is outside the red. The expansion being the red is being trapped by the blue, and it continues on as a negative. So you don't have a lot of field production outside of that connection, which is really, really good when we're talking about plug and play. We don't want a lot of loss. We want streamlining of the plasma current as smoothly without loss as possible. So there isn't a lot of fields being developed there. If you have a capacitor, that's going to cause a backup, and it's going to fill up the space with more of a charge. You're going to get a little more field production around the wires. Change color. there'll be a difference. But it's negligible. It's not multiplying. It's just basically a slow build-up and discharge. And so it'll be almost like taking a breath in and breathing out. Nothing special, nothing great. It just kind of comes in and it goes out as the system pulses through. Stop share of that one. We're going to look at a different circuit and see what happens with it. Go and share to the next one. Share. Zoom didn't grab the command. The next circuit is going to look a little bit different, but it's along the same line. Still one wire coming in. But instead of using 2 wires, we're going to use 1. And it's going to look like this. So in our original, we had our change color. Red coming in at the top. That's the same. But in this one, we're going to make believe that it's a negative. And it's going to go out the bottom like so. You'll notice that I've put in 3 dots at the top. And I want you to keep that in mind because we're going to reference those points later on when we go into the top view. But it's just a 1 wire. And if we go to the next picture, clear that one. Keep that in mind. Share. Go to the next photo. This takes a long time to get everything. We're going to make believe that we put coils on it, just like we did on the first one. But, and just see if we can eliminate some of the confusion with my drawings. This is the top. Current's coming in from that direction. That's your supply. And change colors. Once again, the discharge comes out the bottom. But if we added 3 sets of coil wires and we started one direction and we tapped off, we could actually pick up a current as represented by these 3 lines at the bottom. We can have, if we use this coil with just a wire coming in, we can have a current set up that comes off the top that way. Basically heads back up in reverse. And so we have charge running that way on the wire on the outside. Pick up wire. We have change color. I should do it in order. Do the blue. And because the current's coming down, if we ran the wire on this one the opposite direction, it would pick up a current in a plasma in that direction. Even though the in yellow, with our source coming in at the top, going down through the wire, back up through the wire, across the top, back down again, and out at the bottom, it changes the direction of the plasma in the coils that are wrapping the wire. It's kind of important. Remember, we originally said, change color. Our power came in, our source came in this way, and it left at the bottom. But we end up with this interaction. This interaction sets up fields. And let's clear all and go to the next image. Stop share. Share photo. And all I've done is just added in the interactions of the fields that are now starting to form because we set up coils that are picking up fields from the wire in the middle. We have a toroid on one side. Remember, this one on the left-hand side is making a great big toroid loop that looks like this, coming out the top because it's magnetical and expanding. Nice. We have one in the middle. Well, let's do one on the other side. And that's coming up, and that's coming up, and it's coming out. You have the first one, and it's coming up now. So there's basically a loop here and a loop here forming. But it sets up an exaggeration because you've got these two working against each other. These are going in the same direction, but the one in the middle is the other direction, in blue, is actually going down. It's going in. So you have part of it is coming out on the, let's say the left-hand side is coming out of the top, joining with the one in the middle going down. Clear. So it forms a much larger toroid because of the multiplier. Instead of nothing, 1 on 1, 1 is 1, we have 1 times 1, but 1 times 2 is now doubled. And so you end up with 3 wires, 2 spaces, twice as much going on. Each one of the wraps, if you had a coil around it, each one of the wraps on each of these wires is a multiplier also. So that at the top, if you only had 1 wrap, that would be 1. If you had 2 wraps, that's 1 times 1. If you had 3 wraps, that's 2 spaces times that is 2 times as much. If you had 27 wraps on it, that would be 26 times the potential of the magnifier. And then each one of these, because there's 2 sets of currents, 2 sets of fields running against each other, one is multiplying the effect on the other because they're traveling in opposite directions. So if each one of these had, let's say, 27 turns on it, it would be 27 times 27 times 27. So you've multiplied and made a much bigger, much larger toroid. Clear all. Meaning that you had this big donut that had a hole in the middle. A hole in the middle. Oops. Back here. Come on back. Hole in the middle, sucking in. Wrong color. Sucking into the middle, and a much larger. Quite cool. Let's look at it from the top now. So we clear all. So we have going down in the middle, going up and out, and up and out. And go to the next image. This next one is going to be a top view. Remember those 3 dots? Well, we're going to take a look at just the tops of those wires. And if we look at those, share. We're now looking down and at a slight angle, and we're basically saying we're coming out of the red side, and it's being sucked in to the blue from each direction. And the blue is leaving out the bottom, coming back up through the bottom of the red. So the other part of that, but you still have more happening further out. It's actually making a bigger field on the other half. So we're setting up that infinity loop. Did it too fast? Do it again. We're basically setting up that infinity loop from top to bottom. I'm going to go to the next picture. But you see that we've got one field here. We have another field here. And another field here. And one of the things that I found out when I was getting this lesson put together was that as an artist, I draw all my circles the same way. I'm going to ask you, when you start drawing for schematics, I'm going to clear all, that we go anti-clockwise, do this really, really slow maybe, and go anti-clockwise with the red, anti-clockwise with the red, so that all your magneticals are anti-clockwise, and your blue, or your gravitationals, are clockwise. Not only, this is from the top side looking down into it, the toroids, when they form, they don't come out straight up and straight down. It isn't a simple loop that comes up and around and straight down. It's actually at an angle, and it starts a spin or a vortice. This spin or vortice is noted from the other side, from looking at the top. And you look down, the equator of each of these toroids that we're forming here on each of the leads is spinning at the equator. And in the case of the magnetical, by definition, spins counterclockwise, and gravitational clockwise. This sets up an interaction, if we're looking straight down from the top, of this one feeding the other, back and forth. Let's do that again. Comes in, goes round, and back again. If it comes out in one direction, it goes around the other direction, around the other direction, and back. So there's let's do this again. On the side view, it comes from the top of one into the top of the other and down through the bottom. On the top view, when you're looking at the rotational of it, it's a continuous. So it's anti-clockwise, comes up and around, change color, clockwise. I'm just going to continue drawing clockwise. And then anti-clockwise. So it's basically did it wrong. Goes around and past, and round and past in a loop. It's that training that we need to get into when we start going into three-dimensional visualization of the toroids and how they work, and then how they interact with each other. See if we can get this to make more sense. And around. I'm not going to get any more bogged down than this, but it's that double infinity loop, and it's very similar to how your maggrav coils work on this. So clear this one. Stop share. Go to our next image. And in our last image, we were showing how we had this in three-way, where it comes around one side, goes up and over, comes around, back. Okay, keep that double infinity loop in your mind. On the expansion side, on the magnetical, the plasma fields are radiating outward by definition. So the excess current gets thrown outwards. The excess plasma goes outwards, fills up the space. At the same time, the magnetical, or the gravitational, I should say, is coming in. Oops, wrong color. Gravitational is coming in. And it comes in, comes in, comes in, comes in on both on these two sides. So look at the top, looking down at this. Clear it all. What happens is we get a field that is in addition to the three that are in the middle. We have an additional plasma field that forms on the outside, like so. It basically is, you've got rotation and rotation, but because it gets just a hiccup, it continues on to the other side. Comes around, hiccups, goes on to the other side, and it bypasses the center, just breezes past it. So it gives you this platelet-shaped affair when you have three dots that are set up, one rotating one way and one rotating the other. What happens if we change the orientation of these three dots? So no longer are we in a flat circuit or a single circuit going across, but we're going to change into this other shape. Stop sharing. We go into the beginnings of this next idea. Bring that image up. All we've done is, in this one, we've moved that field down, and when that point down, so we've moved the two magnetical fields closer together, and we've moved the gravitational away from its center point up. Rotations are still the same. And what does this do with our plasmatic field? What kind of field do we make? Is it different? Well, it's quite different. Share screen. And we start to see the delta formation in action. It's also known as the flight system. And so the interactions, and I seem to have got this one upside down, my mistake, are gravitational. In this case, is down here at the bottom, clockwise. Our magneticals, anti-clockwise. Doesn't matter. But where interaction, clear all, is now let that delay go through, is that shape. Clear all. Do it in jagged lines this time. Goes past the gravitational. Goes into magnetical by definition. It's an expansion. Goes back into gravitational. Around. We end up with a field that is forming now because it's a shared field. is a little bit different. Change color. It has that shape to it. By changing the points in our, where we move our transmitters or field generators, changes the shape of the field. Let's see what that looks like. Let's do another example. Takes a minute for these to come up. Let's see. Okay, that was. Oh, no wonder we had to confuse them, sorry. We go to multiple fields, and all we've done is, instead of having two magneticals and one gravitational, we have 3 magneticals and 3 gravitationals. And we draw our lines in around them as indicators to show rotation. So we have 6 points instead of 3 points. Stop sharing. The interactions between these, and on this one, I've left the originals in and I've added in the infinity loop in the middle. And I'll draw it real quick. So you can see and I'm using the one right across from the others. So you have anti-clockwise on the magnetical, clockwise on the gravitational. Oops. Returning it back, so it goes. But not only does it do it directly across, like I show you in this example, but it does it next to each other. So you can have basically this one interacting with that one interacting with this one, and like so, and with each other. So you've got multiple interactions in your field. That's kind of busy, isn't it? Well, yes, it is, and there's a reason for that. We start to look at, when you start to compress multiple fields, it starts changing the shape of the fields. And the easiest way to explain it is it becomes more teardrop shape when you're looking at it from the top. Change color. You have an expansion of the magnetical coming out, and then it tapers down to the center as it goes into the interaction with the gravitational. And you have another teardrop on the other side, and another teardrop on the other side. Stop share, go to the next one. I just really want to jump ahead and say ta-da, but we have to go through this step by step. So we have those teardrops forming. You have one, it has a flat side there, comes out and expands, comes back in, has a flat spot. Has a flat spot, goes out, expands, and comes back in, has a flat spot. Goes out with a flat spot, comes out. Because it's pushing up against each other, magnetical against magnetical, is like 2 positives on a magnet, or 2 negatives on a magnet. They repel each other. Your attraction in blue is in your gravitational coming in from the sides. So your overall field, and I'll let you take a look at it for just a second, and in your mind, you should be able to say, aha, I know what the field's going to look like. We'll do that in pink. And that's this shared field. Goes in just a little bit, comes out, goes to the other expansion, gets pulled in a little bit, the gravitational, comes out around, and like so. We're still dealing pretty much with either flat or simple toroids, but we're starting to change the shape of it. If it's taller, you're going to have an elongation. This is kind of going to look like Mr. Cash's bag graphs that he sells out of Italy. There's a reason for the shape. And I want you to keep in mind when you start looking at some of the stuff that he's produced and the stuff that's is coming out of the factories, there is a reason for each and every one of these shapes. Stop share. Go to the next image. If we go to a standard tube, if you had a pipe, if we had just a pipe in the middle, the field would act just like it was a pipe. If you had plus coming in on one side, it was going in this way, it would produce a magnetical field out like so. On the other side, because of definition, oops, wrong color. You have your negative going out, your field would be collapsing to the inside, gravitation. If you set up a coil at this end and a coil at this end, you would have that same shape. If you took and spread out the thing so it isn't a pipe, so you had spaces in between, you'd have a multiplier. And every space would be one more time what was going to happen in the pickup from the current going on the inside. Remember, you're not counting the wraps, you're counting the spaces, and that's the spaces. So if you had two wraps, that would be one space, would be 1 times 1. If you had 3 wraps, that would be 2 spaces. That'd be 2 times 1. And if you had 4 wraps, that'd be 3 spaces. That would be 3 times in the mathematical analysis. If you bumped up and you put a bunch of coils at one end and they're rotating the same direction, a bunch of coils at the other, you haven't changed anything. You've just added more wraps, and it'd just be more times. If you added 28 more wraps, it'd be 27 more times. If you added 28 wraps at the front end and 28 wraps at the other end, that would be 2 times 28 minus 2 times the whole works. If you stuck one in the middle, it's the same direction. You've just added more coils, more wraps to it. You just still in the, for every time you go around and you add one more space, it's 1 more times what you got in the step up. If it was just a pipe, that would be the same as saying 1. If you make it a coil, each space that you add is a multiplier. Each space that you add is your multiplier. Stop. We got 2 more for these, I think. Takes a minute for this stuff to come up. And I'm going to do a side step here real quick. Bring this image up.
We can design circuits, as many as we want. We can run them in different orientations. This is just another way of representing the counter current from one to the other on the left-hand side, that one there. This one is running everything in the same direction on the right-hand side. So how you set up your wiring, series or parallel, counter current will make a difference in the shape of your plasma field. In electronics, we can mash things together. It really doesn't matter unless we're dealing with radios. We don't have to worry about components being next to each other. We just slap them all together, and as long as the wiring is correct, the circuit works. In the radio circuits, if you put certain components together, you'll get some interference, and it has to do with the plasmatic interactions of those components. Oops, let me go to the next one. I just want you to keep that in mind, because you're going to be able to start looking at your electrical schematics in a plasmatic way and start to determine what it's going to do in a plasmatic circuit. We started with the car circuit, and not a really great drawing. This is one of my early ones. And what I have at the top was a coil, just a regular old coil at the top, and a coil at the bottom, and they ran opposite directions. Just changing direction. One go one way, one goes the other. By definition, the top one ended up being a magnetical outward. We fed it to the inside of it, into the gravitational feed, and forced it down in to be picked up by the other coil going the opposite direction in the center, which was by definition gravitational. And so it took up that gravitational force in the middle, and that goes out the bottom and comes around into the middle again. And that's just another coil at the top. And then we tapped off the bottom. So we had, going back to the transmission, the gravitational, and from the input coming in at the top, from the battery, from the positive terminal, because of an alternator, made it that our current was coming in that way. So it came in the top, spun around, discharged across the spark gap, which had CH3 in the middle of it, was picked up by the gravitational coil at the bottom, and then went back to the transmission to go through the engine and to basically see if it would increase mileage of the cars. So that was the first drawing, and we'll stop sharing that one and go to the next one. Let's see if it looks a little better. And that's basically drawn in a little bit. And what happens is the field that is generated from the magnetical coming out and around and going back in, this is a single coil at the top. This isn't a double. This is not a double mag grab. We used a single coil. We're looking at and see what if we've got some improvements. We're in the first applications. We're seeing on both the Australian test and the American test about 20% increase in mileage. So on if we went, it could go 80 miles on a certain amount of gasoline. Statewide, we're getting 100 miles, 20% more. What happened was we were envisioning, we set up a cyclonic or a tornado flow from the top toroid. Let's see if I can draw this in purple. And that started rotating and around and down, cyclonic or tornado-like vortice. It's also known as an implosion vortice. It's actually taking and shoving things down into this funnel and condensing it. And it's very organized in almost two cyclonic type of motions in there. When you start to see how this thing wobbles and we start seeing the visualization of the fields, you get a vibration, and it basically sucks through the bottom one. The bottom is the gravitational, and it's setting up a draw into the center, and you get a whole bunch of little tornadoes, cyclones coming out the bottom. The power leaves to the cord, goes back to the transmission at the bottom, and at the top comes in from the battery. We're looking at the possibility of the increase in gas mileage as either a slight lightening of the weight of the vehicle because we've created a vacuum at the top, or possibly under thrust theory, a push against gravity from the bottom. Might be that's why we only got 20%, because it wasn't that great. It wasn't that much copper materials in the making. The other thing that we thought about doing, and we're going to be checking with the Australian crew when they get back, is if we turned this whole image 90 degrees and placed the positive end towards the front of the car, then basically what we were doing is forming a series toroid of vortices that formed a vacuum, a compression, a vacuum, and a compression, a vacuum, and a compression, just two, through this, and basically sucking the car forward. And we might end up having actually better mileage by orienting these with the positive end facing forward on the car to suck the vehicle forward. This would be, instead of making the vehicle lighter like Ford Motor Company did with Prius and use the same size engine, do like what Boeing did in the front of their aircraft and set up a way of either moving the air away from the front of the plane or setting up a vacuum and having the plane get sucked into that vacuum. So your plasma, as we keep saying, sucks. It doesn't shove. Jet engines shove because that's on the hot side of the circuit. But when we're looking at fuel economy and stuff, why put a lot of effort into force, which causes friction and heat, going into suction, which causes cooling and motion and creation of things. And so that was the idea behind the car units, was to set up this basically a vortice or a cyclonic effect that actually worked in plasma and sucked the car forward or sucked it up into the air a little bit, making it lighter. Either way, should see a reduction in the amount of gasoline used. So, the last photograph of the series. What would happen instead of using 2, we used 3. And what we end up having is the one at the top is magnetical, expanding out. The one on the inside, more gravitational, coming in. And the one at the bottom, more magnetical,
coming out. Each one of these is multiplying against the other. So if you have, you're basically multiplying A times B times C. You're getting much more out of C than what you put in with A at the top, clear all. This flip in the middle, I'm calling the Frazzle flip. And we're basically inverting the coils. They're all made just the same as they did before, but it's just like if you put all your pancakes on the pancake griddle and they're cooking, you could cook them that way, but if you flip one over in the middle, it's the same pancake, but it looks different. Well, by flipping it over, not only do you change the rotation, which would be anti-clockwise on the top, and it would have been anti-clockwise in the middle and anti-clockwise on the bottom, that one in. We now spin the other one clockwise. And it's not just simple 1 times or 12 times. It can be as many as 9 times. It's 3 times 3, the multiplication. And we start taking a look at this because the plasma runs at angles around it. And this is what causes the spin, it's the angular momentum. Anyway, that's the Frazzle flip. And that is actually going to change a lot of what we're doing in the line of what we're creating in plasma fields. If we had them all going the same way and we just turned this thing over, and I can't rotate these in this particular program. If we turned this image sideways and then added, let's say, instead of 3 fields, we had 9 fields, they would start to resemble the sections of an orange in how they acted against each other. If they were all rotating the same direction and you flipped them to their side, then they would have a shared rotation that would be more like an apple. Okay? And that's the biggest difference between what is an orange with a bunch of triangular shaped wedges in it and an apple, which has got a star shape, has got seeds in the middle, just like the orange has seeds in the middle. But each of the seeds in the orange is located right, I'm not drawing it very good. Those seeds could be classified as your gravitational fields. The fleshy part of the sections of the orange that bulge out would be your expanding magnetical. You get more expansion, and when you run each one at a different phase from the other as you go around. If they're all the same, you have basically just this one rotation, and it's a shared field in your apple. When we take a look at the flight system that is being shown out of Arizona, they're basically setting up an apple because all their magravs are all spinning the same direction. They're all in the same orientation. And this is kind of cool if you're going to have a spaceship that you walk around on the inside. And it would be really cool to see if they could check the fields of their system when they got it up and running, with have somebody walk around between the magnetical and gravitational fields on the platform and see if there's any changes in the outside field. There might be a little bit, but I don't think you're going to have a lot because you're basically setting up a Faraday cage on the outer one. Now, when we took a look at the fields from Arizona,
they were saying, okay, we've got this toroid shape, and they were measuring down, there's like a hollow in the middle. They got it off the ground, they could see that it actually was a full toroid, that looked just like that RBC blood vessel was dipped in the middle. Later on, in some of the more recent ones, they started picking up another field over here. They could read it here, going in and collapsing, it seemed like, into the middle. But it was another one that they picked up here. What they were actually doing was they had their first primary field that was a circle like so. That was the expanding magnetical. They had a gravitational that was coming in the opposite direction, like so. They had their secondary magnetical coming out the top, like so, and coming in at the bottom. If they had long enough ladders and a long enough pole, they probably would find another one here in the middle, another V forming. With the setup that they have, this would be almost like the stems on an apple, going down into the core, this one in the middle. So what they're showing is really, really important, folks, because it's showing that not only do you have a magnetical expansion from the inside coming out in that direction, you have a gravitational coming from the outside down into the middle in the opposite direction. When we see this on our magnets and stuff, when we view the magnetic fields, that there's iron filings on the magnetical and nothing in the gravitational, and they're all lined up one end to end all the way around in that. And there's also the secondary fields that form magnetically, and more of them. And these that are harder to perceive, but they could actually, where your first ones could get stopped by walls and stuff of the building, the second ones could actually be expanding out past the building because they're more energetic. They're coming out of the center and going out past and coming back in. So kudos to the Arizona team. I'm really pleased with what you're showing. It follows in with the drawings and the visualizations that I have on plasma fields. I wish you guys all the success, and hopefully this will give you an idea of how to increase your fields or start setting up the different types of fields, whether you want a cherry, a big pit, and a small plasmatic field. Do you want an apple, which has got a whole bunch of little gravitational fields on the inside and a bigger field on the outside? Or a peach that has a single pit and a big space on the outside? Or an orange or a grapefruit, which might even give you a larger field, but you have more interactions. And you might find that you have actual walls start to form inside your spaceship because you're changing the directions of the vortices of the flow of the plasma in the toroids. So I'm going to clear all this and bring us back to our main group from the Plasma Frontier and open it up for questions and comments.
I have a question for you. Can you be more specific about flipping that center coil, and what does this change? What are the possibilities of it?
In your magraphs, you've got them all set up the same, and it probably worked really fine in the electrical side of the circuit. There's actually 3 things that we're building all at the same time and not realizing it. You have an electrical, you have a flight, and then you have a power generation. By flipping the center coil in your maggrav system, you may be changing it from an electrical component to a flight system. And it may take, that's all you may need to do is just flip that center coil in its entirety. And it's reversing the fields. It's making the middle field basically grind like gears against the upper and lower. So B of the middle coil is grinding A and C above and below in opposite directions. And instead of having a simple 3 times the amount, you have a x to the third multiplier, which is considerably more multiplication of the fields. Where you tap off is going to give you different things. And as we go, we're going to start with shortly in the next video, we'll be giving the assembly of the car units, and we'll be showing Patrick's pin, which is a big improvement, we think, in the system, and go from there. But right now, with the preliminary tests with the car units, we're at about 20% increase, where there should be none in the old automotive way of looking at fuel savage. So it's interesting. It's not as much as we wanted. We're going to take a look and see where there's been other successes and where they've doubled their mileage, and see where we possibly messed up. I rushed in getting mine assembled and placed in my vehicle. The car runs fine, it brakes fine, everything works fine. I had only one incident where I really had to slam on the brakes, and it was a little dicey on that one. It felt like everything was coming apart. And I don't know if it was just because it's an old vehicle or that I had forward momentum more than I had anticipated. I don't know. So we're going into the second tank of gas on it. This is city driving, and see if we have the same improvement. So I don't know if that answers your question.
Do we have any potential for like a generator or anything with any of this technology?
Yeah, because when we go to our dynamic core, and that's going to be the next build, one of the next ones. We'll do the car unit next, so folks know what's coming up. Simply because it's the progressions. It's the easiest, least expensive, most safe thing. You can't muck up things. You're not dealing with high voltages. You're dealing with 12 volts. You're dealing with circuits that aren't connected. You're strictly dealing with plasma. It's a real safe, cheap, inexpensive, and it looks like cost effective. So for under 20 bucks, you can build a car unit and slap it on and save right off the bat at least 20%, and we're hoping more than that. I think there's a possibility. We get into the dynamic core, which we've alluded to. If you dropped it into your MagGrav, because of the shape, the way it's set up, straight from the factory, you're probably looking at a generator unit right there, just dropping the static core into your MagGrav. Unplugging from the grid because there's some problems. But yeah, Joe's showing just dropping. Go ahead and talk, Joe.
This is just the mock-up. So let's say this is your MagGrav. This would be a part of the dynamic core, and it would fall right in the center of your MagGrav. And this is what we've been working on behind the scenes for several months now, and we worked a lot of the bugs out of it. And I believe we got a really good jump on it. And the only thing made it possible was the Frazzle flip. And that's very important. That's why I pushed the issue here. I'm sorry I did that, Frazzle. I apologize. I know you didn't want to say
no problem. I know it's interesting because it changes. It's like we're dealing with the same components. We're dealing with the same circuits. And as I say to my team, I says, yeah, they call us innovators. We're research and development. We're R&D. We do a lot of looking at patents. We do a lot of research. We're trying to figure out how other systems work, and why we had success in the Alex beads, why we had success in the Douglas refrigerator units, why we've had success with the Peruvian car unit, which is what we're going to be talking about on the next videos. There's a reason why there's successes, and they stayed with pattern. They started using the same circuits, and it's knowing what part of the circuit that you're working on. And let me see if I can see Mike's. I did it again. I put away all my examples, and I don't have them sit here close. I'll do it real quick. A pair of scissors, and work this Okay. We have your piece of wire, and you wrapped it together. You have this loop, that's your circle. We gave it a twist. We called it an infinity loop, okay? You twist it again, and you're starting to talk about doing coils. This is where your spark gap is. When we talk to Mike, Mike talks in symbols, okay? You can take him literally, but you're better off saying what he's giving you is a symbol. Now we take this same thing and we bend it in half like this. This is your maggrav, flat stacker coil. This is a jewel ringer circuit, same thing. This is your Alex's beads, same thing. This is your Douglas generator circuit, same thing. It's the same basic shape. It hasn't changed since 1888. It's the same shape. It's used in hundreds of different appliances under hundreds of different patents. It's the same circuit. We're getting back. It's like, why is this important? It's part of everything that we're working with. It has to explain, it helps explain how the plasma fields interact. It explains how coils interact with one another, how step-up transformers work, how step-down transformers work, how maggrav units work, why they work, why the fields are formed, okay? I talked really briefly about implosion vortices. Cleve, you want to jump in on that one real fast? I love putting you on the spot. You have to unmute yourself, Cleve.
Oh, I thought a shake of the head would mean no. It is a topic that I would encourage people to start to research for themselves, because in the end they are their own best teacher. But it's a whole breed of science we've not looked into or not been able to look into. Powers to be have guided us into the other side of the whole science, which is called explosion technology. So everything we have is about explosion technology, which is about force, deterioration, friction, heat, wear, and it's kind of that side of things. Whereas implosion technology is life-giving, and it's all the other things. It's anti-wear, anti-friction. Anti-friction. That's a misnomer, isn't it? It's what else can I say about it? The work
It's organic.
Again, it comes back to the work of Victor Schauberger. He was the Tesla of nature, and he used nature and implosion technology in his devices, and he talks about it a lot. Now the problem is that, and it's not a problem for European people, because he spoke German. So a lot of his work for us Westerners, that we rely on the translators. And there was a guy called Callum Coots from Australia, Byron Bay. He wrote 3 or 4 books where he translated them, and they're available online, and so are some videos online from him. And I advise people to really just look into implosion technology and vortices, because plasma is a fluid and behaves just like water or air or any other fluid, and it travels into vortices and it implodes, and that's where this energy is. So it's beyond my scope to teach it in 5 minutes without sort of thinking about it, and then having prepared some things to look at. So
it was unfair on my part, but I just wanted people to know that part of the work that we're looking at is the other half of the equation. You have an expansion and you have a contraction. Yes. The Western civilization has been playing with expansion, the explosive portion of it. Why? It's a lot more fun. It's like it's right there in front of you. We take all the subtleties of the recycle, the collapse, the gravitational, the the shrinking back down, and it happens almost on its own without any x-ray, just like, okay, we go back to it. So this forms a suction, this forms a vacuum, this causes a pull, and instead of pushing yourself through space, you're being pulled through that space. You're being sucked along. And so you don't have the acceleration things you have. It's more of a deceleration, I imagine.
And that's where I was nearly going to cut in on your lecture, because I had a bit of an aha moment. Remember, I've been dicing back and forth about which direction has got the suck for a wee while, and I'd settled on the flow being from the magneto in, but actually it's the gravitational that's causing the suck so when you look at a water spout, it's the gravitational sucking the air right down to the bottom of that water spout. Right?
Exactly.
And so we actually got them all facing backwards. We should be putting the gravitational in the air to make it lighter, because that's where it's sucking from.
Maybe we can always try it. It's in the.
So I
gotta
think
see which works.
I think we got to trial it out. We got to turn them around and trial it.
See what happens. At worst, it makes it worse. You end up with 4 miles to the gallon instead of 10.
Yeah. Well, conversely, I mean,
we got that one wrong. Maybe we can do it the other way and get it better.
Well, I mean, if that's the fact, then the increases we've got is been counteracting the disadvantage of what we've done there, and it's the nano coating and other plasmatic forces that work that are still causing some improvement.
Right. So there's a lot of questions, and in science, the more questions you answer a question, this just gives you 5 or 6 more questions to answer. You got question one, you got one question answered. Well, great. Now you got 5 more, and that's the fun part of this whole adventure. Is I didn't even look at that possibility, and it starts your mind working in other directions and other possibilities, and you start to see that it's not just this little point. It's not just this little part. It's not just the maggrav. It's not just the dynamic core. It's not just the car unit. It's not just the electrical generation. It is a combination of all of these working together. And it's what part do you need of this giant machine to do whatever that you need to do. You don't need the whole machine, the function of the whole machine at a time, but you need bits and pieces of it. And it's almost like a tractor. Sometimes you need the hydraulic lift in the front. Other times you need the wheels in the back to push it forwards. And then every once in a while you need our takeoff the side, something else. So where do you attach what device to your main machine gives you what you want. And so what I'm hoping with this lecture series that we've been putting together is that people start to think about the whole picture, or realize that it's not just that one little part that they're working on. It is actually, a very large thing. It's like, wow, we've been working on the entire ship at once, and all I was working on is the power supply. When it comes together, you start seeing this thing as a whole 3-dimensional object, or possibly a multi-dimensional object at later times. Who knows what we're going to find on the next app. Joe, comments? Oh, we've got one more.
I got one more. Just before we go on, I was saving it for last, but this is getting towards the last anyhow. I was going to throw it out there for the community to get involved with these talks a bit more, and put their comments in if they think we're wrong, or if they think they've got a bit more to add, or if they got questions, post it online and get involved with this, because I've never learnt so much about plasma in the last month or two as once we started this sort of involvement with each other, and you end up bouncing off, and we all gain. So
and I highly encourage those of you that are watching is to actually put together groups of your own. You need 3-4 people. That way, you're bouncing ideas off of each other. not only are you learning, but you're also teaching. And each of you bring to the group a bit of expertise that the others don't have, or different perspective, or different look at it. And realize each person has an idea, they have a part, they may have a piece of the puzzle, and it's just trying to figure out where that piece is. It's like having one of those jigsaw puzzles with 1,000 pieces, and look at it, and you look at it, and you look at it, and you go like, what? And then it goes, oh, you take 2 pieces over, you give them a quarter turn, and it all goes together. And you go, well, I've been looking at those 3 pieces for them, and it didn't go together. And they say, I just had to turn them, and you had to flip them over. And that's where you bring in your fellow workers, or people that come in and share ideas, your teammates. And I highly encourage it. It's amazing what you learn from each other, and the bounce off, the interaction. Joe, have any comments?
No, it's like before you guys covered basically everything. And the only thing I got to add, if anybody has something they want to share, they want us to look at something, they have an idea, just pass it along. We communicate. We always communicate. We always try to advance and learn and share everything that we can. And I appreciate everything that's been going on. Everybody's been working really, really hard, except Allison. You know, she's been slacking off. But other than that, we're okay. You know,
No. On Allison?
she's
Allison! You know, we love you, girl. You know, come on.
Hey, I did my ice stuff.
Okay.
That was an eye opener. Doing the freezing of the ice with the stone and the magnets. I didn't share that with everybody here yet. We looked at it earlier before Joe got in there, but I don't know if you want me to share it. It's pretty interesting.
Why don't you got that one really clear picture? The one that went around the stone?
Yeah, hold on a sec.
Why don't you show that one? Joe's been doing quite a bit of freezing water with different gowns and stuff, and has had the problem they have it doesn't show up well on photographs. It makes a big difference when you do it yourself, and when you put it in the freezer, good and hard, take it out and then let it sit in the cabinet in the sink for an hour or so, and let it melt gently. And then that way you can see it without the frost and stuff on the outside. Allison actually took my advice on this one and boiled the water and tried it. And it removes some of the opaqueness of the ice when you do it, and you see more of fields. So try it both ways. Try it boiled water and also with just regular tap water or distilled water, doesn't matter. And look at the difference. Try to do one thing different with each one of the ices. So go ahead and talk, Eston. You've got your picture up.
Okay. So this was just using a stone that was saged, nano-coated, wrapped in copper, and then frozen on top. So we went from there. Let's see if I can get through this. What was interesting is how it rose. It did the arc. I think Joe mentioned that before. And in the arc, it also made a perfect bed right around the stone itself. And I actually had this stone where it was not touching the ice because I had it encased in the baggie. So it was above the ice. So it actually drew towards it when it started freezing, and then created this bed around it up here. So that was just kind of a, interesting situation. So that was just more of it, how it formed the bed. I don't know if you guys can actually see this very well, but, and then this was the outcome on one side. Then I did a circular. That's better. So that was kind of fun.
Mm-hmm.
And it had the 3, it was toroidal here, and the 3, and that.
It's really interesting.
Sorry.
Yeah, what was interesting about that is you're dealing with not only a stone, a crystalline stone, but also with the wire. They've got some nano coating on it. What's fun is the freezings that we've done so far is the shape of the coils. The nano-coated coils will make a difference in the shape of the field in the ice. And then when you add other items to it, you start seeing other changes. And in the case of this one, it actually sets up this three-sided shape inside. And so it very complicated pattern work, but yet uniform and cohesive. It's like you see the intersections of the fields that were frozen. Good job.
Thank you. The magnet one was interesting also, though, because it created two different sides. It created walls perpendicular from each other. So that was just really interesting, the way that it froze with the magnet on top and on the bottom freezing. This is the top of that one. It created this circular outer area and then solid in the middle.
How many magnets did you have in the bottom?
I had 7 magnets, hematite magnets, only because that's all I had, and 8 on top.
Okay, because if I squint, I'm actually seeing sharpened edges where they're kind of flattened, which is hexagonal or octagonal in shape, which is cool. And
see how it went. See if I can find a better one. You'll see there's an actual wall here. See how it's a wall it created on each side, right down the middle.
And that's basically a fracture in the ice. It's a break in the ice, but it happened to form on opposite sides, on polar opposites, which is kind of interesting. So you end up with basically 2 sections of orange out of, instead of an 8 section, but at least a partition forming between the fields. And so you have a flattening between the two and rounding on the outside edge. So it's kind of an interesting shape. It would be interesting to see if, in fact, we can freeze it and have the ice form the cracks that have separated in the walls to where it looks like an orange or looks like a grapefruit. That would be very interesting to see if that could be possible, on a small scale like in refrigerators. So, good work. Fun stuff.
I think what I was looking for was to see fields without GANs being used, using different items and that kind of thing.
You'll get that with metals, and I'll tell you something. If it's freezing, it's almost frozen. You touch it, the energy from your hand is shatter the ice. When you touch that, you'll hear it snap. You'll see that. That always puzzled me. I did it several times to make sure it wasn't just a fluke. You'll try that. The more you freeze, you're going to learn a lot more because you'll start reading the fields. It's really cool. There's a lot of different effects.
And when we get into visualization of fields, this is part of the confirmation of what we've presented as theoretical. What Alice is showing is basically practical application. How does it show up? This is what Joe's been trying to get everybody to do, is this is the theoretical. Now let's show you the practical. Let's show you what actually happens in reality, and we're using water as a media to show it, to freeze the plasmatic fields. So these two have been harping on everybody to freeze it, it's really fun. Yes, it is.
Great
Anything
way
else,
to
Allison?
introduce. No, that's all. I'm working on some others I'm gonna start playing with, based on your suggestions earlier, and looking forward to that.
It's you might want to try put saran wrap on top and just a drop of water of GANs. There's different GANs at different times on different water. And when you're doing solution, I always put a little food coloring because it's just a lot easier to read the fields. You see a lot more. So if you want to try that, you can.
Thank you.
No problem.
I just out of ins and chuckles because I just got all my CH3 GANs nicely clean, And I was sitting there going, oh, I've got extra CH3 liquid, Iquist. And I dumped probably, a tablespoon into a cup of tap water, threw it in the freezer. The entire cup was opaque.
Oh.
It completely changed the look of the water, just that little bit of CH3 GAMS water. And that was pretty dramatic difference. And so small amounts is probably better. I was like, oh, let's throw it together and throw it in, see what happens. It was pretty impressive.
Speaking of a little bit doing a lot, I'd like to I've been meaning to post this anyhow, so I'd like to release it here. That I created a soda bottle plasma battery with CO2 and zinc ganses, and a little bit of nano-coated copper wire in there, and a few choice pebbles to weigh it down, and filled it up with water and chucked one in the reservoir. And it didn't take long before the field appeared in the taps in the city. I won't say where it was. And anyhow, I did the Australia's longest river the other day, and it didn't take too long before it was in the taps too. So I'm after people, because now I can't tell, because my freezer has a permanent plasma field in it. I can't tell whether something has a field or not, because there's always a field there. So I'm after a bit of feedback from people living along the Murray, if they can grab a sample of some Murray water and freeze it and post that online too. That would be exceptionally good. So people in Australia, Murray River. Thanks, guys.
And it isn't that you're putting the GANs, they're actually just in the field.
Yeah, just in a small soda bottle and chuck it in, and it does many kilometres in a couple of days. Like I can't judge. It turned here. It was about 34 kilometres in 4 days, and it was at my tap.
Wow.
So downriver, and it's pumped locally off the river here. So I put it up 34 kilometres upriver, like 4 days earlier. So
all right. Any other questions or comments?
But I also encourage people to do their own waterways, because that's a sure quick way to send healing to your community. And it's once you've got that field established, it's there it's there pretty much forever. And so people's bathtubs, their showers, everything starts getting a plasma field in it, all their food. Quick way to change the world, people.
Yeah. Anyway, thank you for all you that have donated to the Plasma Frontier. We really appreciated your donations. It helps keep us operational. It pays for the bandwidth. We thank you greatly, and you guys have a great day. Donations for those ones in the comments below. Let's go. Oh, he's going to click goodbye.
No. I stopped the recording. Cleve is still recording.